Good morning. Welcome back to the module Communication Theory, Learning Outcome 4, Topic 13. So, in this topic, we are going to study about digital continuous wave modulation. Okay, before going to discuss today's topics, we just recall the previous session topics. In the previous session, we studied about amplitude modulation with the noise. After that, we studied angular modulation with the noise. In amplitude modulation, we are using two types of detector, such as synchronous detector and the envelope detector. Similarly, in angular modulation, we are using two types of detector, like phase detector and the frequency detector. Because angular modulation basically classified into phase modulation and the frequency modulation. And then finally, we derived the expression for destination signal to noise ratio for both amplitude modulation and the frequency angle modulations. Okay, so today topic we are going to discuss about digital continuous wave modulation. So the way we are calling it is a continuous wave modulation means the input signal for this digital continuous wave modulation is a rectangular pulses. Example, we can use the non-return zero unipolar rectangular pulse or non-return zero bipolar rectangular pulses as a input signal for this modulation. But if you see the digital modulation techniques, the input signals are binary bits, either it is zeros or ones as a input signal. So there is a basic difference between the digital modulation techniques and the digital continuous wave modulations. Okay, so digital signal. So digital signal means it is a process of converting analog information such as voice and videos into a digital signals, digital forms. Okay, so the other form of digital signals, example, text messages, computer files, and programs, all are come under the digital informations. And the digital data it has the broad spectrum band and it has the significant low frequency content. And mainly this kind of the continuous wave, digital continuous wave modulation used in long haul digital transmission applications. Example, the cable line transmission and the telephone line transmission and so on. So the by using digital signal as a input signal, we can modulate either amplitude or frequency or phase of a sinusoidal carrier wave. If you consider the input signal as NRZ rectangular pulses, means non-return zero rectangular pulses, then the output signal means the modulated signal, it is switched its amplitude from one discrete value into the another discrete values. So here the input signal we are calling as a modulating signal and the output signal is a modulated signal. So this here shows the various type of modulation waveforms. The basic digital modulation waveforms, ASK, FSK, and PSK. So amplitude shift keying, frequency shift keying, and the phase shift keying. Then the last waveform shows the double sideband with the baseband pulse shaping. And in this modulation, we are considering the input signal as a binary data, either zeros or ones. You can consider the ASK modulation when the binary input one is entering into the modulator, then the switch is on and it allows simply the carrier as it is. Whereas the binary zero is entering into the modulator, the switch is off, so that there is no carriers present during that binary zero information. So in such a way, the ASK modulated signal will be generated. Since the switch is on and off, the modulation is modulated signal is generated due to switching on and off. It is also called as on-off keying techniques. Coming to the second type of modulation, FSK modulation, frequency shift keying. In this case, when the binary bit 1 is coming, then it allows the carrier with frequency FC. Whereas when binary 0 is entering into the modulator, the carrier frequency FC will be shifted to some other frequency, so that which is compared to which is less compared to the original carrier frequency. So in this way, the FSK modulated waveform will be generated. Okay, and then the third type, PSK, final phase key modulation. whenever there is a changes in the input sequence, like 0 1 or 1 0, there is a 180-degree phase shift is occurring. You can see here when the first two bits 1 0 is changes, so that there is a 180-degree phase shift occurring. If there is no changes in the incoming binary bits, you can see here third and fourth bit 1 and 1, there is no changes in the phase. So in this way, there is the phase of the carrier will be changed whenever the incoming bits are changing, either 1 0 or 0 1. Then 180-degree phase shift will be occurring into the carrier signal. Such kind of modulation you can call it PSK modulation. And then the last type of modulation is double sideband PSK modulation. So in this case, we are varying the phase as well as the amplitude of the carrier signal. You can compare to PSK. In PSK, the amplitude is constant, whereas double sideband, the amplitude is varying depend on the modulation parameter. This equation shows the basic modulated baseband signal representation in quadrature form. Here we can see that there is a carrier signal AC cos omega t plus theta is the carrier signal, and in that the xi of t xq of t is the message signal which is present in link phase and quadrature carrier. Okay, in this the carrier signal frequency, amplitude, and phase we are maintaining as a constant. But the XIFT, XQFT give it's a message signal to modulate the carrier signal. And if the in phase and the quadrature components are statistically independent, and at least one of the component, if it is has the zero mean, then the spectral analysis will be easy. So the equation shows the power spectrum of the baseband modulated signal. You can see there are 4 terms present in the power spectrum of baseband modulated signal. The first 2 terms coming from the in-phase component, lower sideband and the upper sideband, and then last 2 terms coming from the quadrature component, lower sideband and the upper sideband. And if you consider if you find out the power spectrum of the baseband modulated signal after passing through the low pass filter, and we can minimize the power spectrum which is asymptotically equal to GI of f plus GQ of f. Okay, it's the low pass power spectrum of the modulated signal. By using this formula, we can modify the power spectrum of the baseband signal, band pass signal. Okay, the GLP of F minus FC means the lower sideband low pass spectrum and the upper sideband low pass spectrum. Okay, so this equation shows the relation between band pass spectrum and the low pass spectrum. From the low pass spectrum, power spectrum, we are getting the band pass power spectrum. And here we are using the in phase and the quadrature component. Now we can consider the in phase component of the band pass modulated signal for MRA digital information. So it is xi of t is the summation of the all the amplitude levels of the rectangular pulse p of t. Here the AK indicate the amplitude levels of the rectangular pulses. Okay, here the AK represent the sequence of source digits. Okay, it is actually the amplitude levels of the rectangular pulses with rate R equal to 1 by capital T, where capital T is the duration of the rectangular pulse. And here we are assuming that the source digits are equiprobable, statistically independent, and uncorrelated. Okay, so the key modulation techniques in this method is NR is at rectangular pulses. So this waveform shows the various type of the rectangular pulses waveforms, like NR is at unipolar, NR is at bipolar, R is at unipolar, R is at bipolar, one sister, and so on. So if you see the NRZ bipolar unipolar, it will have only the positive level. But NRZ bipolar, it has both positive level and negative levels. So in this way, the rectangular pulse waveforms are generated, and it is used as a input signal for digital continuous wave modulation. So the mathematical representation for the rectangular pulses is P d of t asymptotically equal to U of t minus U of t minus t, where capital D is the duration of the rectangular pulse, and it has the one within this interval 0 to d, but it does not include 0 and t. For example, if you put the time t equal to 0, it becomes u of 0 minus u of minus t, so it really becomes 0. There is no output. And similarly, if you put time t equal to capital D, then it becomes u of t minus u of 0. In this case also, the value becomes 0. So in between 0 to t, the function PD of t having the value 1. So in that way, it will be the rectangular pulses are operating. And by taking the Fourier transform of this rectangular pulse, we can get the sinc function for the respective rectangular pulse, which is denoted by d squared sinc squared of ft. And we know that the pulse duration d is inversely proportional to the input rate r. So we can replace d by 1 by r. So finally, we are getting the power spectrum for the rectangular pulse 1 by r square sin squared of u by r. This is the expression for the power spectrum expression for the rectangular pulse. It may be either the non-return zero or return to zero. Either it is a unipolar or bipolar waveform. Okay, so now we'll discuss about the amplitude modulation. So the basic amplitude modulation, the digital amplitude modulation is binary ASK. It is generated by simply tuning the carrier on and off. So that we are also called as on-off keying technique. ASK modulation also called as on-off keying technique. If you go with the MRA ASK modulation, then there are M-1 discrete amplitude levels will be generated with the on position and the off position. Okay. Set the Q component of the bandpass modulated signal Xc of t equal to 0, and take the ith component as a unipolar non-return zero signal. We can get the information from the in-phase component only. Okay, so even though the modulated signal containing both the in-phase and the quadrature component, we are considering the quadrature component. We are not considering quadrature component. These quadrature component signal will be useful to estimate some other parameter of the received signal, like what is the carrier phase there is carrier phase and carrier frequency, and some other parameters will be estimated from the quadrature part. The information will be extracted from the in-phase component, so that we are not considering the Q component in the received signal. So the ith component we can written as ith means the in-phase component can be written as xi of t is summation of the various amplitude levels of the rectangular pulse PD of t. The various amplitude level is ak, which is equal to 0. It varies from 0 to m minus 1. If we consider the m different amplitude levels or m different symbols. So for that rectangular pulse, we can find out what the mean and the variance. So the mean of the different amplitude levels of the rectangular pulse is MA. It is also mentioned as AK bar equal to M minus 1 by 2. And the variance of the rectangular pulse is sigma A squared, which is equal to M squared minus 1 by 12. So we can find out the equivalent low pass spectrum, and that is a GLP of F for the rectangular pulse. By using that mean and the variance, we can finally derive the low pass power spectrum for the rectangular pulse. So you can see that in the resulting band pass spectrum, Most of the signal power contained within this range Fc plus or minus R by 2, where R is the input bit rate. Okay, the input source bit rate is R, and the power spectrum of the rectangular pulses are decreases, which is proportional to second order. It is decreasing as a second order flow law, which is proportional to F minus Fc power minus 2. So the estimated bandwidth Pt approximately equal to R. R is the input rate. So this waveform shows the ASK power spectrum. X-axis is the frequency, y-axis is the magnitude, and the bandwidth is Pt equal to R. It has the range Fc minus R to Fc plus R. If an MRASK signal represent the binary data at the rate Rb equal to R log to M. So here we are relating the input rate with the bit rate. Okay, the bit rate will be varying based on the when we go with the higher order modulation, so that the input rate is multiplied with the log to M, where M is the number of symbols. Okay, and we can write the bandwidth of the modulated signal Bt approximately equal to Rb by log to M. So where Rb is the bit rate, the transmit bit rate divided by log to M. So by using that the log to M, by dividing the bit rate by the number of symbol, we can able to observe the what is the bandwidth of the modulated signal. Because when we go with the higher order modulation, the automatically the bit rate going to be increasing. By dividing the number of symbol, we can able to get the what is the actual bandwidth of the modulated signal. Okay, so and similarly, if you take the ratio of the bit rate to the bandwidth, it will give the how many symbols are present in the particular modulation, so that it is approximately equal to log to M. So this ratio of bit rate to transmission bandwidth serves as our measure of modulation speed or spectral efficiency. Then we can generate the another type of modulation, which is called the quadrature KM or QAM. So in this we can combine the two binary ASK modulation with the different phase levels. We can generate the quadrature amplitude modulated signals. Okay, so the binary QAM transmitter, the polar with the polar binary input at a rate R equal to Rp by 2. So what this means that you can see from this the block diagram of the binary QAM transmitter. There are two channels we are using: in phase channel and the quadrature channel. And the incoming input X of t, it has the input rate R, that R equal to bit rate. So bit rate and input rate are equal in this case, and the incoming signal is the PPSK modulated signal. ASK binary ASK modulated signal, it has the two levels, and then it is passing into the serial to parallel converter. Okay. Um, so the AK equal to plus or minus 1. Here we are considering. Okay. So then the rate of the in phase channel and the rate of the quadrature channel will be half of the bit rate. So that is RB by 2. RB by 2 we are using as a rate of the in phase channel and the rate of the quadrature channel. Which means, for example, the incoming bits are 1000 bits are entering into the serial to parallel converter. Then the 500 bits are entering into the in-phase channel, and 500 bits are entering into the quadrature channel. So then it will be multiplied with the carrier signal cos omega ct, and by by shifting that carrier by 90 degree, we are getting sine omega ct. Okay, so here the carrier will be multiplied with the incoming bits. Then finally these two, the in-phase and quarter signal will be added together. Then the resulting output signal is XCMT. It's a quadrature amplitude modulated signal, where in-phase and quadrature modulating signals represented by Xi of t and Xq of t. You can see here in this the amplitude levels is for in-phase A to K, for quadrature it is A to K plus 1. It is a general expression for in-phase component and quadrature component. If you put k equal to 0, it becomes a0, it becomes a1 for quadrature. And we can vary. If k equal to 1 means a2, a3, a4, a5, a6, a7, and so on. Like that, in the data will be splitted and given into the in-phase and quadrature. So here the duration of the rectangular pulse is d equal to 1 by r, the reciprocal of the input rate, or it will be equal to 2 times of bit duration. So the rectangular pulse duration is 2 times of bit duration for QAM modulation, because we are giving giving the input rate for the input and quadrature channel as half of the bit rate. So that the duration of the rectangular pulses are 2 times of TB bit duration. Okay. And the AK equal to plus or minus 1 is the amplitude levels for the incoming bits. The peak modulating values for in-phase and quadrature, there are only two levels maintaining positive and negative values. That is the duration for the time. Okay. This waveform shows the binary QAM signal constellation diagram. There are four signal points present: 0, 0, 0, 1, 1, 0, 1, 1, and then each points are representing one symbol in the QAM modulation, uh, and it consists of the two bits. It also known as the bits. So you can observe from this constellation diagram, the symbols having the only two amplitude levels, either it is a plus one or minus one, and the symbol also having the four phases. Okay, like 45 degree. This is 45 degree. 90 uh, plus 45, 135, and so on. So like that, all the four symbols are maintaining the different phase levels. So in QA modulation, the amplitude as well as phase of the carrier signal will be modulated. So the in phase and quadrature components are independent, but they have the same pulse shape and the same statistical values. It means the mean value equal to 0 and the variance equal to 1. So this is the mathematical expression for low pass power spectrum of QA modulation. It will be equal to 2R modulus of PD of f squared. So the PD of f squared is the power spectrum of the rectangular pulse. We know it is 1 by R squared sin squared of f by R. So just we can replace. But we know that the relation between bit rate and the input rate for the QA modulation. So the input rate is half of the bit rate for QA modulation. We can replace R by RB by 2. So 2 into RB by 2. And here also we need to replace the R by RB by 2. So 4 by RB square. By simplifying, finally we are getting the power spectrum for the QA modulation. 4 by RB sin squared of 2F by RB. So then the ratio of bitrate to bandwidth, it will give the 2 bits per second per hertz, because each symbol in QA modulation consists of 2 bits. So the bitrate is twice the bandwidth. And that's why we are getting the 2 bits per second per hertz. Okay, as a number of symbols present in the uh, It's a spectral efficiency. Okay, the spectral, you give the spectral efficiency for the particular modulation. Okay, then the ASK and the QAM spectra actually extend beyond the estimated transmission bandwidth. So this modulation, ASK modulation and the QAM, they have the spectrum, power spectrum of this bandwidth is beyond the allocated bandwidth. So this is called spectral spillover. So to avoid this, is the spectral spillover means outside of the bandwidth. Okay, some powers are spreaded outside of the bandwidth, which is called a spectral spillover. But by using the bandpass filter at the transmitter, we can remove the spectral spillover. However, by the filtering is more, then it introduces the ISI in the modulated signal. So the one way to control the spectral spillover and improve the spectral efficiency is by using a vestigial sideband modulator. So in this vestigial sideband modulator, we are using the two filter. One is the Nyquist low pass filter and the vestigial sideband filter. Okay, so that and we can allocate the bandwidth for the vestigial sideband is B equal to half of the input rate, not B equal to R. It is half of the input rate and plus some the vestige band is vestige band due to that Nyquist low pass filter and vestigial sideband low pass filter. So this is the final expression for the bandwidth of the vestigial modulated signal, VSP modulated signal, R by 2 plus beta n plus beta B. So this beta n beta B is the edge bandwidth due to that the leakage of the power. From this waveform, you can see it's a power spectrum for the VSP. Okay, the actual bandwidth is only R by 2 for the VSP. But due to the leakage of power at the edge of the spectrum, we are considering that that is beta V and beta N. So the total bandwidth for the VSP equal to R by 2 plus beta N plus beta V. And we know the relation for the bit rate and input rate is R equal to RB by log 2M. So we know the for VSP R equal to 2 beta t because beta t equal to R by 2. We are assuming this 2 is negligible. So beta t equal to R by 2. So R equal to 2 beta t. You can replace R equal to 2 beta t. Then we can get the ratio of bitrate by bandwidth till minimum less than or equal to 2 times of log 2M. So this diagram shows the VSP transmitter modulator. Okay, so there is an income signal XRT. Then we are using the Nyquist low pass filter. Okay, to control the spectral spillover. Then the signal is modulated by carrier signal using local oscillator. And then it is again passed through the another low pass filter, that is a VSP filter. Finally, we are getting the VSP modulated output signal XCRT. Okay, using this AM modulation and VSP modulation, means ASK modulation and VSP modulation, we can see one example. So the problem is the binary data is to be transmitted on a 1 megahertz carrier. Spillover is not a concern, but BT must satisfy the fractional bandwidth constraint. That is the ratio of BT by FC less than or equal to 0.1. Estimate the maximum possible bitrate RB when the modulation is OOK or binary QAM or VSP with M equal to 8. So the question is we need to find out the bitrate RB for the different type of modulation. Okay, so we know the BT by FC is less than or equal to 1.0.1. So from that we can find out what is the BT. So BT equal to FC into 0.1. So 0.1 FC is carrier frequency is given in the problem 1 megahertz. Substitute 1 megahertz equal to 10 power 6. So we are getting 10 power 5. So 10 power 5 equal to 100 kilohertz is the bandwidth for this modulation. And we are considering that BT is the input rate. That is 100 kilohertz. Okay, actually 100 kilobits per second bit rate. Okay, then the bitrate formula is RB equal to R log base to M. For OK modulation, the number of symbol is 2. So we can replace M by 2, then log 2 by 2 equal to 1. So for OK modulation, the bitrate RB equal to 100 kilohertz. Means that the bitrate and the bandwidth are same. Okay, we'll go with the QA modulation. In QA modulation, the number of symbols is 4 symbols for binary QAM. So M equal to 4. So it becomes 2 into R. So 100 kilohertz into 2 equal to 200 kilohertz is the bit rate for the binary QAM. So here the unit is not kilohertz, bits per second per hertz. And then the last another modulation, VSP modulation. For that modulation, the number of symbol M equal to 8 is given in the problem. Substitute M equal to 8, we are getting 3 times of R. So the bit rate equal to 300 kilobits per second for VSP modulation. Okay, next we are going to discuss about the another type of the digital continuous wave modulation, which is called phase modulation. Okay, so this is not the analog modulation; it is a digital modulation because we are using the digital rectangular pulses. Okay, so we can see that the binary PSK waveform which contain the two phase level, either plus 5 or minus 5 for the binary PSK modulation. For it has only two symbol, one symbol maintaining the plus 5 radians, another symbol maintaining the minus 5 radians. Okay. Uh, for MRA PSK signal, we are using the phase shift pi k, then the k varies from 0 to n minus 1. So, okay, so this equation shows the mathematical representation for the PSK modulation. Okay, so here the cos omega CT plus theta is the carrier signal. PD of T is the rectangular pulse. AC is the carrier amplitude. Here the pi k is the phase of the phase changes in the carrier waveform. So this pi k ensures the PSK modulation. So depend upon the type number of symbols, the phase of the carrier will be varying. So the trigonometric expansion of the cosine function, we can get the in-phase and quadrature component for this PSK modulation. So the in-phase component is xi of t, quadrature component xq of t, pd of t is the rectangular pulse. It is separated by kd. Here the ik and the qk is the phase of the in-phase and quadrature component. So the ik equal to cos pi k and the qk is sin pi k. And we can generalize the phase shift of the carrier waveform is pi k equal to pi of 2 ak plus n by capital M. Here the ak is the power level, amplitude level of the rectangular pulse. It varies from 0 to m minus 1, where m is the number of levels. So which ensures the number of symbols for the modulation. And the capital N we can usually considering either 0 or 1. For the phase changes, for phase 0 means we are not considering the initial phase. One means some initial phase shift is present. So this waveform shows the constellation phase modulation constellation diagram for two different modulation like 4 PSK modulation and the 8 PSK modulation. So in 4 PSK modulation, there are four symbols are present. And we can see these four symbols located in four different phases: 0, 90, 180, and to 230, and so on. Okay, and the amplitude of this PSK is constant. Only the phase is changes. And we can see here is the 8 PSK modulation. In 8 PSK modulation, okay, there are 8 symbols are present, and each symbol consists of the 3 bits for 8 PSK. For 4 PSK, each symbol consists of the 2 bits. And the simple, if you generate the symbols in with respect to the amplitude levels, it can generate the equal probable symbols with the positive negative values. So the mean of the in-phase quadrature component, that is IK bar QK bar equal to 0, and the mean square value of the in-phase quadrature component equal to 1 by 2, cross product of the in-phase quadrature component equal to 0. So in this way, the symbols are generated for the PSK modulation. Then the power spectrum for the PSK modulation, same formula here also we are using, like the QAM, 2 into R by 2, PD of F modulus of PD of F squared. We know that the power spectrum for rectangular pulse, we can substitute. Okay, so the PD of F squared is 1 by R squared, sin squared of F by R. So already R is present, so the 2 will be cancelled, 1 R will be cancelled. Then this is the final expression for the phase modulation. And we can modify the PSK modulation as a OQPSK. So OQPSK means orthogonal quadrature phase shift keying modulation. So in this, what we are doing, it is like a QPSK moderation. Only thing is, in the quadrature channel, we are introducing some delay with the duration TB, where TB is the bit duration, so that the modulated phase shift is occurring in the OQPSK moderation. The modulated phase shift occurs every TB seconds because the quadrature channel signal will be delayed by TB seconds. So the delayed signal is multiplied with the carrier signal, then it will be added so that we are generating the orthogonal, sorry, not orthogonal, offset keyed QPSK modulated signal. Okay, then we are going to discuss about the frequency modulation. So here we can see there are two kinds of modulator we are using. In the first diagram shows there are n number of local oscillator present. The incoming signal is x of t. The incoming signal x of t control the switches of the this modulator, frequency modulator. Okay, so depend upon the incoming x of t, the switch will be connected to the respective local oscillator. So in this way, the FSK modulated signal will be generated. So the digital signal exactly controls the switch that can select the modulated frequency from the bank of n oscillators. Okay, but in this case, there is a discontinuity is occurring at every switching instant time t equal to kd. And unless the amplitude, frequency, and the phase of each oscillator has been carefully adjusted, the resultant output spectrum will contain a relatively large side lobe, so which don't carry any information, additional information, then and thus it wastes the bandwidth. So that we have to in this first type of FSK modulator, we have to take care about the adjustment of amplitude, frequency, and the phase. Coming to the second type of FSK modulation is continuous phase FSK. Here we are using only one local oscillator and one input signal, and then the input signal is modulated with the local oscillator by using frequency modulator. Finally, we are getting the modulated FSK modulated output signal XC of t. So in this case, there is no discontinuity in the carrier phase. Okay, we are getting the continuous phase FSK signal. Okay, so we are assuming that all local oscillators are having the same amplitude EC and the phase theta, and but the frequency are varying with respect to the amplitude levels of the rectangular pulse AK. So the general expression for the frequency of each of the local oscillator is Fk. So Fk equal to Fk is a shifted version of the carrier frequency. So Fc plus Fd plus Ak. So the here the Fd is the shifted frequency, Fc is the carrier frequency, and Ak is the amplitude level. The Fd is changing with respect to the Ak values. So Ak is plus or minus 1, plus or minus 3, and up to plus or minus n minus 1. Let m the number of levels m equal to even number, then we can write the mathematical expression for the frequency modulation. So in this carrier waveform, that is cos omega ct plus theta, and the omega d akt ensues the frequency modulation. Okay, here the omega d equal to 2 pi fd. Okay, so here the parameter fd equal the frequency shift away from the carrier frequency. So the frequency shift of the carrier frequency depend upon the amplitude levels ak equal to plus or minus 1. So let's consider the binary FSK modulation. So number of symbol m equal to 2, and the duration of the rectangular pulse equal to the bit duration. Both are equal, which means the rectangular pulse duration and the bit duration both are equal, so that it is inversely proportional to the bit rate. And we are considering n equal to 1, and this is the formula for the rectangular pulse. And here the frequency, this FB is the same as the FD, the frequency shift of the carrier signal, which is equal to half of the bit rate for the binary FSK. For the binary FSK, the shifted frequency FB equal to half of the bit rate. So after trigonometric expansion of the FSK modulated signal, and by using this fact A equal to plus or minus 1, we are getting the in phase and the quadrature component of the FSK. Okay, because the omega d, we know the omega d equal to 2 pi fd. Now for in phase component, we can replace the omega cos omega d akt, and for this the in phase quadrature component, sin omega d akt, it is equal to ak sin omega dt. In phase component and quadrature component, and we can substitute omega d equal to 2 pi fd or 2 pi ub for the FSK, binary FSK. So here the cos omega DAT equal to cos omega dt. So omega d equal to 2 pi fd or lp, and fb equal to rb by 2, half of the bit rate. So cos 2 pi rb by 2 t. So finally we get the cos pi rb t for the in phase component of binary FSK. And the quadrature component of the, so it is a cosine function in phase component. Then the quadrature component xq of t is ak sin omega dt. Substitute omega dt and multiply the rectangular pulse. Then this term, the ak sin pi rbt modeled, okay, modeled as the rectangular pulse for quadrature component. So we are not considering the phase for the quadrature component. The phase information considered only for the in phase component. Okay, that's the difference. And the qk equal to minus 1 per k ak, the amplitude levels. So from this in phase and quadrature component, we can see the final expression. For in phase component, there is the cosine function present, but for the q component, there is no cosine function, only the rectangular pulse is present. Hence, the ith component means the in phase component being a sinusoid, it contributes some spectral impulses at the frequency of r plus or minus rb by 2. But the qth component contains no impulses, since the average value of the qth component equal to 0, there is no the cosine function present in the final expression for the qth component. So the mean is 0 and the variance equal to 1. So for the FSK modulation, the power spectrum is depend on the in the impulse of the in phase component. So that is a del of f minus rb by 2 plus del of u plus rb by 2. That means the impulse occurring at plus rb by 2 and minus rb by 2. in the in-phase component plus RB into the rectangular pulse power spectrum. Okay, so here the P of the power spectrum for the rectangular pulse. Okay, since here we are using that in-phase component, the sync function depend on the in-phase component. So this is the final expression for the rectangular pulse of the FSK modulation. So this waveform shows the power spectrum for the binary FSK modulation, and the frequency shift FD equal to RB by 2, half of the bit rate. You can see here the bandwidth for the binary FSK modulation ranges from FC minus RB by 2 to FC plus RB by 2. If you take the difference, it will be equal to RB, the bandwidth equal to bit rate. And the power is roll log, which is inversely proportional to F1 is FC power 4. Thank you.